I'm Žiga Lučić, and I will present joint work with Matija Pretnar on local algebraic effect theories, which was developed to aid with reasoning in languages with effect handlers. When reasoning about programs, we often rely on certain equivalences, such as the ones stemming from mathematical properties. For instance, the functions f1 and f2 can be considered equal since x plus x is equal to 2 times x. Program equivalence gets much harder when we start using computational effects. For instance, when using print, it's not entirely clear whether printing the same string twice is the same as printing a doubled string. We do not know whether the language adds a new line separator at the end of each output, or perhaps the prints are counted for a message log. We must therefore know the specifics of the language implementation. So just imagine how much more difficult it becomes if effect behavior is user-defined. This is precisely the case in languages with algebraic effect handlers. In such a language, effects are modeled by operations which are assigned types in the so-called effect signature. For instance, here we have an operation choose that represents a binary choice. It accepts a unit argument and returns a Boolean value. The operation itself is only a construct, and its behavior is specified by the handler that intercepts the operation call. The choose_true handler has an effect case for choose, and here we have the unit argument of the operation call and the program continuation k, which is captured at the time of the operation call. The effect case states that whenever choose is invoked, the continuation is resumed with the value true. This causes every call of choose to simply return the value true. Now, when using this handler, the behavior is crystal clear. The code always returns 1 because choose always returns true. And for a slightly more interesting example, if we build a function choice that returns one of its two arguments, where the selection is again done by choose, we can again use the handler that always returns true, and in that case, choice always chooses the left argument, so the functions f1 and f2 are equal, since, well, they both always return 0. They're also equivalent in a broader sense. Every handler that results in an associative implementation of choice results in f1 being equivalent to f2. So another instance of a suitable handler is one that collects all possible results. And on the other hand, if we randomly select one of the options with a 50% chance, that is not a suitable implementation. The main issue here is how exactly to state such a property. One way to do that is to use equations. In the original approach to effect handlers, the theory consisted of an effect signature and equations between operations. For instance, associativity of choice, which is what we wanted in the previous example, can easily be expressed with an equation. Using equations allows us to abstract away from concrete implementations. We can focus on effect implementations that satisfy certain requirements that are set by the equational theory. The original approach assumed a single global effect theory, but this turned out to be very restricting. There are many useful handlers that work with entirely different theories, and by fixing a global theory, we're unable to use some of them. This is where our work comes in. We transition to local theories by packing equations into computation types instead. A computation type now states the type of return values, the names and types of operations that may be called, and the equational theory. At this type, all computations are considered equivalent modulo the equations E. Let's take a look at a small example. In this signature, we define an operation signal that accepts a unit and returns a unit. It really does nothing more than just signal to the handler that it was called. And in the effect theory, we can be a bit more expressive. The equation states that if we signal twice and then proceed with an arbitrary computation z, it's no different than if we signal only once and then continue with z. Now, an example of a handler that fits the equation is one that returns true as soon as a signal occurs and false if the computation is evaluated without a single signal. And an example of a handler that does not respect the equation would be a handler that instead returns the number of signals received. We can now use this equation to restrict possible effect implementations. Here we have two functions, f1 and f2, and f1 has no equations while f2 uses the above equation. This means that f1 can be handled by any handler for signal, while f2 requires the handler to not differentiate between one and many signals. We can of course use such handlers for f1 as well, but not vice versa. This already shows a difference between global and local theories, since in the global setting, we either require all handlers to respect the equation or none of them. In the first case, we can't use such a wide variety of handlers for handling f1, and in the second case, we can't use the equation as a reasoning tool in the body of the f2. And when implementing effect behavior with handlers, we of course need to be mindful of the effect theory that we're working in. The handler type informs us about the kind of computations that the handler is used for and what the resulting computation type is. Since two computation types are involved, equations occur in two spots. The E on the left sets the requirements for the implementation, and E prime on the right states the theory of the outgoing type. We have to check that for every equation in E, if we handle both sides, we end up with equivalent computations. The equivalence is considered in the theory of E prime, so we may be aided by the equations that are packed in E prime. Handler correctness is undecidable, so the proofs are constructed in a logic that is coupled with the type system. Using equations comes with extra work when typing handlers, but provides a strong tool for reasoning, and it's a very natural fit for algebraic effects. Local effect theories impose less restrictions than global ones, and we consider them an all-around improvement over global theories. Equations are vital for reasoning about effect behavior, and the type system can also be coupled with different kinds of logic, so we can use a system that fits the problem at hand. If we use local effect theories, the changes to the language are rather minor, and the resulting system is also easy to use. We do not need to switch to denotational semantics or to a full-fledged dependently typed setting. The drawback is clearly the need for user input when typing handlers, but handler definitions are the only point where this is required, so most of the work is still automated. Since the paper was published, we have done some considerable advancements. We have extended the language with recursion and some basic data types, just products or lists. We also included the non-trivial extension of subtyping, which greatly improves the usefulness of the language. All of this has been formalized in the Coq proof assistant alongside some smaller examples, and we also constructed a sound and adequate denotational semantics, which takes into account all the before mentioned extensions. The approach was also implemented on top of the F framework. We decided to use a bidirectional type inference as it's more suited for working with effect theories. But the system does not automate correctness proofs, which are left to the user. The proofs can be done by pen and paper, or they can also be constructed in the Coq formalization of the language. We also considered a few future goals. The important extension that has not yet been done is polymorphism. We wish to have types that are polymorphic in the value component, as well as polymorphic in the signature and equations. The extension could be far from trivial, but it's ultimately important if you want a language that can be used in practice. Another key aspect that we're not yet entirely satisfied with is proving handler correctness. Automation would be great, but even just easing the burden by providing better tools for user proofs would be a great start. Perhaps also very important is finding good use cases for local effect theories. We feel that we are now at a point where future work should be guided by shortcomings when trying to apply it to actual problems. Anyone interested is welcome to read our paper, and thank you for your time.